Welcome to the Base Face Network.
Lesson 6. Mean and Variance of Discrete Random Variables. Definition. Given a discrete random variable x, the mean denoted by mean is the sum of the products formed from multiplying the possible values of x with their corresponding probabilities. It is also called the expected value of x, and given a symbol, mean is equals to e open parenthesis x close parenthesis is equals to summation of I, p open parenthesis x is equals to I close parenthesis. Recall that empirical probabilities tend toward theoretical probabilities, and in consequence, the mean is also a long-run average. This can be observed from the result of the activity. As the number of trials of a statistical experiment increases, the empirical average also gets closer and closer to the value of the theoretical average. Inform learners that this is why we can interpret the mean as a long-run average. That if you have 3 coins tossed, and if all coins are fair, then they would have 8 possible outcomes, like HHH, HHT, HTH, HTT, THH, THT, TTH, and TTT. And if they would repeat tossing these coins 8,000 times, they would expect 1,000 tosses of each of the outcomes, and thus the expected frequency of 3 heads would be 1,000 tosses, of 2 heads would be 3,000 tosses, of a 1 head would be 3,000 tosses, and no head would be 1,000 tosses. If we average this, we would have open parentheses 1,000 close parentheses, open parentheses 3 close parentheses, plus open parentheses 3,000 close parentheses, open parentheses 2 close parentheses, plus open parentheses 3,000 close parentheses, open parentheses 1 close parentheses, plus open parentheses 1,000 close parentheses, open parentheses 1 close parentheses divided by 8,000 is equals to 1.5. Although the mean is called an expected value, this should not be interpreted as the actual expected result when they do an experiment. In the example for tossing 3 coins, the mean is 1.5. Point out that when you toss 3 dice, you cannot get 1.5 heads out of it. This indicates that the mean is not necessarily a possible value of the random variable. So learners cannot simply say that the mean is what they expect to be the number of the heads when they toss 3 coins. Rather, it is to be interpreted as a long-run average. Mention also to them that the mean is the value that we expect the long-run average to approach, and it is not the value of the random variable x that we expect to observe. Recall that the average of a given set of data is a measure of central tendency. Inform them that the expected value being an average measures the center of the distribution of the possible values of x. The mean of a discrete random variable x can be given as a physical interpretation. Suppose we imagine that the x-axis is an infinite seesaw in each direction, and at each possible value of x, we place weights equals to the corresponding probabilities. Then the mean is at a point which will make the seesaw balance. In other words, it is at the center of gravity of the system. Examples of finding and interpreting the mean and variance. Number 1. Example with biased dice. Recall the biased 6-sided dice with a probability distribution for x. The number of spots on the upward face when the die is rolled given as follows. So we have here the formula, which is the P open parenthesis x is equals to I close parenthesis. In table 1, we have 1 minus 0 divided by 6. In table 2, we have 1 minus 0 divided by 6. And also in the third table, we have 1 minus 0 divided by 6. In table 4, we have 1 plus 0 divided by 6. And the fifth table, we have 1 plus 0 divided by 6. And lastly, in the table 6, we have 1 plus 0 divided by 6. The expected value of the distribution may be calculated as follows. So we have here again the formula, which is the mean is equals to E open parenthesis x close parenthesis is equals to summation of I P open parenthesis x is equals to I close parenthesis. So if we will apply the table, this will be the result. Is equals to 1 minus 0 divided by 6 plus 2 open parenthesis 1 minus 0 divided by 6 close parenthesis plus 3 open parenthesis 1 minus 0 divided by 6 close parenthesis plus 4 open parenthesis 1 plus 0 divided by 6 close parenthesis plus 5 open parenthesis 1 plus 0 divided by 6 close parenthesis plus 6 open parenthesis 1 plus 0 divided by 6 close parenthesis is equals to 7 plus 30 over 2. If Q is equals to 0, then this reduces to a fair dice, for which we would have a long run average of 3.5 for the number of spots on the upward face. Example number 2. Practical example used in insurance. An insurance company sells life insurance of 500,000 for a premium or payment of 10,400 per year. Actuarial tables show the probability of normal death in the year following the purchase of this policy is 0.1%. What is the expected gain for this life insurance policy? There are two simple events here. Either the customer will live this year or will die, a normal death. The probability of a normal death as given by the problem is 0.001, which will yield a negative gain to the insurance company in the amount of minus 489,600 is equals to 10,400 minus 500,000. The probability that the customer will live is 1 negative 0.001 is equals to 0.999. Thus, the insurance company's expected gain X from this insurance policy in the year after the purchase has the following probability distribution. Gains 10,400, outcomes is live and the probability is 0.999. Gains minus 489,600, the outcomes is a normal death and the probability is 0.001. M is equals to open parenthesis 10,400 close parenthesis open parenthesis 0.999 close parenthesis plus open parenthesis minus 489,600 close parenthesis open parenthesis 0.001 close parenthesis is equals to 9,900. Learners should take note that if the insurance company were to sell a very large number N of the 500,000 insurance policies to many people, with the long-run average profit per insurance policy is 900, the company would be expected to make a total profit of 9 times, which is 9,900. Whether a measure of central tendency is the only relevant summary measure. Remember that for a set of data, we also need other summary measures, such as measures of variability. Learners have already met the concept of variance and standard deviation when summarizing data. The variance and standard deviation of a set of data are measures of spread. Random variables also have a variance and a standard deviation. The variance is derived by getting the expected value of open parenthesis x minus u close parenthesis 2 where u is the mean. To illustrate, go back to the table on flipping 3 coins and get the number x of heads in these 3 coins. Now add the 2 columns with the following heading in bold. See below and fill the corresponding values.
The total in the last column is called the variance of the random variable and the square root of 0.866 in the standard deviation. Now, define the variance of a random variable as a weighted average of square deviations of a value of x from the mean. Where the weights are the respected probabilities, the variance, usually denoted by the symbol, is also denoted as var x and formally defined as. The variance gives a measure of how far the values of x are from the mean. Ask the learners what is the variance is when x is a constant with probability of 1. Learners should be able to say that it is 0 in this case, just as it was in the case of a set of data that does not vary. In non-trivial case, when there is more than one possible distinct value of x, the variance will be a positive value. The bigger the value of the variance, the farther the value of x get from the mean. Define the standard deviation as the square root of the variance of x, that is. Example of gains in life insurance. The following calculation for deviations form from subtracting the mean from the gain, as well as square deviations and weighted square deviations. The variance is the sum of the entry on the last column, while the standard deviation is the square root of the variance. The standard deviation is more understandable of the two measures of spread, since the standard deviation is in the same unit as x. For example, if x is a random variable representing the number of heads and 3 tosses of a fair coin, then the unit for standard deviations is heads, while the variance is in square heads. Unlike the mean, there is no simple interpretation for the variance or standard deviations. The variance, though, is analogous to the moment of inertia in physics, but that is not necessarily widely understood by learners. Stress that, in relative terms, a small standard deviation in variance means that the distribution of the random variable is quite concentrated around the mean. A large standard deviation and variance means that the distribution is rather spread out, with some chance of observing values at some distance from the mean. In practice, the variance is not computed with the definition but rather using the following result. Thus, the variance is the difference between the expected value of x squared and the squared of the mean. Explanatory note: this can be derived from the definition, some algebraic expansion of a binomial expression, and some properties of expected values, such as the mean of a constant is the constant mean of a continuous random variable. What they think would be the expected value of x if x were continuous with probability density function fx. They should provide the equivalent quantity for a continuous random variable involving an integral. That is, the mean of continuous ex random variable x with probability density function fx is. Integrals may be viewed as sum if the curve is discretized. Also tell them when looking at a probability density function, they can locate the mean by determining the center of gravity of the curve, where the pivot should be placed to make the probability density function balance on the x-axis. Imagining that the probability density function is a thin plate of uniform material with height fx at x. An important consequence of this is that the mean of any random variable, continuous or discrete, that has a asymmetric distribution is always on the axis of asymmetry of the distribution. For a continuous random variable, this means the axis of symmetry of the probability density function.